Good afternoon, everyone. My name is Amanda Ormond. I'm a consultant with the Four Corners Wind Resource Center. Thank you for joining our webinar today. Since you all were on time, we're going to go ahead and get started. This webinar is called Wind Energy, a Good Citizen of the Electric Grid. Really pleased to have two of the folks that I think are the top expert in wind and renewable energy integration in the country with us this afternoon. We're going to have two presentations. Our first speaker is going to be Mark Ahlstrom. Mark's the founder and CEO of several different technology companies. For the last 15 years, he's been the CEO of WindLogic, who I believe is one of the nation's leaders. Well, it is the nation's leader in applied meteorology, wind energy analysis and forecasting, as well as integration. Mark has served as a technical advisor to a lot of different leading organizations in renewable energy, including the Utility Variable Generation Integration Group, known as UVIG, ICAAA, which is the National Electrical Standard Setting Body, OEA, and also the North American Electric Reliability Corporation. So we're going to hear from Mark first, and then we're going to hear from Jim Caldwell, who I'm going to introduce now. Jim is the Senior Technical Consultant to CERT, the Center for Energy Efficiency and Renewable Technology. Jim has 50 years of experience in the energy industry, in both academic and the industry. For the last 30 years, he specialized in renewable energy technology and project development, and I don't think we know many people that can say that. He has worked in the past for Atlantic Ridgefield. He's had key positions in Los Angeles Department of Water and Power, and he has worked as a technical advisor to trade associations and DOE and a host of other organizations. So we're really pleased to have both these gentlemen with us today. So we're going to start off with Mark Ahlstrom, who's going to provide kind of an overview of some of the things that wind technology can do and renewable energy technology can do. So I'm going to go ahead and hand it off to Mark.
Thank you, Amanda. It's a pleasure to be with you here today. I'm going to give you some of my views around best practices of integrating wind and where it's going in terms of future reliability support from wind as well. As Amanda mentioned, you know, the group WindLogic that I'm with, we really started out helping wind project developers do a much better job by applying a lot of meteorology and weather modeling to the problem. We were acquired by NextEra Energy Resources in 2006, and today we've become really an analytics shop. Our mission is forecasting and optimization solutions to enable low-cost, reliable, and sustainable power systems. So we're working throughout the whole spectrum now, especially around integrating renewable energy. Our parent company, NextEra Energy, is the largest owner, operator, developer of wind in the country. So a fair number of the projects that you see around are actually developed and operated by NextEra. In terms of integration, we often think that wind is some sort of very different beast. When you actually look at a lot of our conventional generators, like coal plants and gas turbines and so forth, it turns out they all have a lot of quirks. We've become pretty used to these, but for example, with a lot of these like large coal plants, you have to start it up a day ahead if you're going to want to run it today. So you can't just start them up on a dime. Once you start plants like this, they have to run for a certain number of hours before you can even think about shutting them down without damage. And once they're started as well, they have just a limited operating range. So it's kind of chunky. If I start this plant, I need to run it at least half of its maximum output all the time, and then I can ramp up above that. But the rate at which I can ramp will also tend to be fairly small. So it can't be moved around on a dime. With wind energy, it's a different problem because we're really driven by the characteristics of our fuel source, and the wind, of course, is driven by the weather. And so we have this sort of variability and the challenge of forecasting exactly how much the output will be at a given point. So that tends to drive it. But it's much a case of that. It's still challenging, but in a just a kind of a question of degree. It's not a totally unique problem. In fact, the way that a lot of this is dealt with, to take all of these different types of generators and mesh them into a system that can match the amount of generation we need at any point in time, is really done through what they call the process of unit commitment and dispatch. And what I mean by that is that unit commitment is often in the day ahead time frame, where you are figuring out, what is my load going to be tomorrow at 1 o'clock, and then I have to make sure I have the right set of plants available to me, and some of those plants I might have to start today. Now, once I get to real time, where I'm getting close to 1 o'clock, then I use a process called dispatch, which is, a lot of people, you'll hear about, well, this plant is dispatchable, and ironically, people often talk about nuclear plants as dispatchable. And a lot of people think that means, well, I can turn the dial to whatever I want at any point in time. And that's not really the case at all. We just talked about these constraints. Dispatch is not just arbitrarily turning the dial. It's really looking at all the different generators that are available to you and optimizing those by moving them around through usually a 5-minute adjustment process called dispatch, in order to get a perfect match between the amount of generation that I have and the amount of load that I'm trying to meet. Now, it turns out that wind actually is very dispatchable. In fact, all of the market regions that are sometimes called independent system operators, ISOs, are dispatching wind in one form or another today. And they actually include wind using a forecast in the day ahead unit commitment, so they look at the total mix of generators they'll have available. And then they're often giving wind a 5-minute dispatch set point, an instruction about here's how much I expect to get from you for this 5-minute period. Well, how do they do that if wind is so difficult to forecast precisely? Well, it turns out that forecasting wind day ahead is much like the weather forecast on TV, but forecasting wind for the next 5 minutes is actually a lot easier. Why is that? It's because wind actually has a lot of mass. The air is very heavy when you really look at it, and you are then spreading this across dozens of turbines that are covering many square miles. And it turns out that inertia of that mass of air and the smoothing you get over the wind turbines in a plant actually means that the output of a wind plant is quite smooth and quite stable. If it's producing 100 megawatts right now, I'm pretty sure it's going to be producing almost 100 megawatts 10 minutes from now, for example. So that's what's called a persistence forecast. It's just assuming that whatever it's doing now is going to continue to happen, and that works surprisingly well for wind, especially if you are doing that within the next 5-10 minutes. It's a very good forecast, and that's how these ISOs are actually using it in the 5-minute period. Now, they can turn wind down if they have a reason for doing so by dispatching it to a lower point, and wind plants can follow that change very, very quickly. The thing to keep in mind is that wind turbines are among the most modern of the generators on the fleet, and because they run with state-of-the-art power electronics and state-of-the-art controls, they can follow that dispatch point very precisely. Obviously, you're limited by the total amount of energy you get from the wind in that period, but you can do up to that level or anything below it very, very precisely. So this is really one of the best practices that has come out of a large body of integration studies that have been done. There's need for shorter scheduling intervals and to dispatch all generation into these shorter intervals. Other ones that Jim will be highlighting in a few minutes as well is that it helps to use a larger balancing area, because the error of forecasting one single wind plant, like in the day ahead time frame, will still have a fair amount of uncertainty around it. But a lot of that is just the forecast kind of random errors, that will tend to average out. So by just aggregating, say, a dozen wind plants over a state, I can reduce that total forecasting error by about half. So one of the best ways to make wind more predictable and have lower uncertainty is to use larger balancing areas. Obviously, though, if we're going to optimize the whole system, we want to get more flexibility from everything on the system, both conventional plants and the wind plants. And we want to integrate these forecasts for wind into our day ahead and our real-time plans, as we described, because you can't pretend it's not there. We're getting enough on the system where you have to forecast it, and you have to know how much wind you expect to be there and work around that. And Jim will be talking more about some of the other causes and incentives about the system and flexibility. In many cases we have flexibility out there, but because of maybe contracts or market rules, we're not using everything that's even available to us. So that's kind of when things are just operating normally, we just do that sort of dispatch process. But as a system operator, you also have to think about, how am I going to make sure that the system stays reliable even when things go wrong? For example, we call these a disturbance. If you unexpectedly lose a large generator, like a big coal plant or nuclear plant or a big transmission line, you have to make sure that you can automatically adjust for that and keep the lights on. And that basically falls into three sorts of categories. One is that we need to keep the frequency very close to 60 hertz here in North America. If we deviate from that, it causes damage to lots of types of motors and other equipment. We have to also control the voltage and keep it at, within the right range, because the voltage control allows that energy to move around the system efficiently and is also needed to protect equipment. And you have to make sure that even if something does go wrong, that the generators that you need to provide frequency, voltage, and the power for the future periods stays connected to the grid. You don't want it to automatically disconnect just because there was a little dip in frequency for a few seconds. So these are often called reliability services. And this gets into a lot of the work that's being done by NERC, the organization that controls the reliability standards and so forth. Let me explain just what a disturbance is, because maybe you've not thought about this. But if we're starting out here at 60 hertz, as you see on the left, if I suddenly lose a large plant, which can happen in a fraction of a second, frequency immediately starts to dip, because now I don't have enough generation to meet my demand, to meet load. And so it kind of slows down the other generators and the frequency starts to fall. Well, it's important that you have some generators there on the system that will automatically detect that drop in frequency and very, very quickly start injecting additional power into the system to slow down that rate of fall, turn it around so it's coming back the other direction, and get to a stable point. And you're talking here just in a few seconds, so a lot of this has to be kind of automatic or pre-programmed into the generators out there, that they are automatically watching frequency and responding in this way. This is often called inertia, or in the very fastest sense, or primary frequency response in the next few seconds. Now, after you have that automatic, pre-programmed sort of response, then you can start adding additional power through instructions that come from the system operator out to the generators through what they call automatic generator control. It's every few seconds, or getting into the 5-minute dispatch process and putting more generation on. And that allows you to push the whole system back to the 60 hertz frequency. It turns out that wind plants actually can do all of this very, very well. We haven't always been asking them to do it, because we've mainly just been looking at earlier wind plants, as a source of clean energy, and not so much detailed control of the power, the instantaneous sort of delivery of that energy. But all modern wind plants now are, and have been for years, providing voltage support to maintain voltage at the correct level where they're connected. That's basically a standard feature in all of today's wind plants. They have the capability of also providing that sort of automatic primary frequency response that we just saw. In fact, this is already in place in Texas and the grid down there, and it's an option you can get for any new wind turbine, essentially. You can even get what they call synthetic inertia, which is interesting. For example, if I'm already producing as much power as the wind will allow me to, then I don't have additional power to use for primary frequency response to nudge it back up even further. Well, it turns out if you're on a system like in Hydro-Quebec, where they actually thought they wanted more of this very quickly, sub-second kind of injection of power, you can even do that with a wind turbine, because the spinning blades and generator of the turbine itself have a lot of inertia. They're pretty heavy, and you can take that kinetic energy, and with the right electronics, you can turn that into a quick burst of additional power, even if you're already producing, your maximum power output and haven't backed down to save room for that. So that's available as well. Now, all of these are, these do have some additional costs, or they may cut down on the amount of regular energy you sell to the grid. So you don't want to use them, without coordinating with all the other generators on your system to make sure you're using the best ones at the current time to get what you need. But the capabilities are there, and there's a lot of discussion right now around, should wind at least be installed to have these capabilities, and then should there be some sort of market products or payments, to allow wind to be providing this to the system as well. So the key point to take away here is that, wind plants really are power plants. They are dispatchable, as long as you do it right with a, a very short-term forecast, like 10 minutes ahead or less. You can very well fit these into the 5-minute dispatch and expect wind to follow that quite closely. They ride through disturbances extremely well. The voltage can go all the way down to 0 volts, for a period of time, and the wind turbines will stay connected and help the system after that as well. They can provide frequency response and voltage control and do it very quickly, very accurately. And they actually can ramp and adjust their output faster than just about any other thing on the grid. You can go all the way from 0 volts all the way to the maximum that you have wind for in a fraction of a second if you want. And in fact, in some cases, they actually slow down wind in terms of limiting its ramp rate, because that's so much faster than a conventional unit that they have to be ready for that. Finally, I just wanted to put in a plug here that if these are the sort of things that you really are interested in from a fairly technical point of view, Amanda mentioned the organization called the Utility Variable Generation Integration Group, UVIG, and the website is shown here on the screen, uvig.org. This is where a lot of the utilities and system operators and consultants and weather forecasters and market designers go and have literally 2 or 3 days of in-depth discussion around these topics. Next meeting is coming up in April in Sacramento. And so if you're a utility or a co-op or somebody who is really interested in kind of the engineering and technical issues around integration of renewables, UVIG is certainly a resource at their website, and you might want to consider checking out some of their meetings and attending. So with that, I will turn it over to Jim and go into a lot more detail around some of these issues in a real study. Thanks.
Thank you, Mark, very much. We're going to take a couple questions. I have a couple that came in, and I think I have one question on the webinar. If you are interested in asking a question, we're going to take a couple questions now, and then we're going to take some more at the end. Either raise your hand or click the question button, or please feel free to type your question into the chat box. So a couple here. One is, when you were talking about that wind has capabilities for dynamic reactive power, frequency response, and synthetic inertia, you said that there is additional cost to be able to access these services. So the question is, how do these costs for capitalizing on these services from wind compare to the cost from other technologies, other resources?
Sure. The incremental cost of installing these features in a new wind turbine, if you're planning ahead for it and you're doing it for a new one you're building, the cost of adding these features is fairly small today. It's something, but it might increase the cost of the turbine by 1 or 2%. The real cost, though, is in your real-time operations. I mean, obviously, in most cases, wind is under a contract or used by a utility to deliver as much clean energy as possible to the grid. So you're trying to usually max out your delivery of energy, the kilowatt hours that we need. And if you have to reduce the amount of energy you're delivering in order to save headroom, to save additional output, like for ramping up or for primary frequency response in that upward direction, then that would reduce the amount of energy that you're selling and getting paid for. So there would be a cost, what they call an opportunity cost, of basically lowering the amount of energy you're delivering, on a normal basis in order to have that capability. So you don't want to do that unless you really have a value in doing that, and maybe you would get in the future you would get paid in another way for doing that would make it worthwhile. But under current contracts and current usage, usually you would not want to pay that cost as long as the system could get those reliability services from some other type of generator. Other sorts of responses don't have much of a cost. Like the voltage support, typically does not have a high cost, and so that's usually provided all the time by wind plants as well.
Okay, sounds good. Now I have tried to unmute Kelly Francone's phone. So Kelly, if you're with us, do you want to ask your question? Okay, I'm muting her again, and I'm going to see if Sarah Probst wants to ask a question.
Hey, Amanda. I had a couple of questions. One was whether dispatchability for wind is different in the WEC than in an RTO.
Well, it certainly doesn't have to be. I mean, as I pointed out in the slide, or maybe I didn't point it out at the bottom, you don't have to be in a market region to do dispatch. I mean, every utility operator is doing some sort of, real-time fine-tuning. Sometimes it's a lot faster than 5 minutes. In some regions, I think including WEC, actually do it, much more quickly in the order of seconds. So the issue is, not all regions expect wind to follow a dispatch or give wind a dispatch set point that they're supposed to follow. Some of the older wind plants, of course, didn't really have the capability of following that because that does take additional equipment and communications to get that signal from the system operator and then respond to it. But most of the new wind plants being installed today going forward are installed with that capability. And in some of the regions of the country, you have kind of a differentiation where, like, old plants maybe before 2005 or whatever, are not assumed to have that capability. But most of the newer ones are encouraged to install it and to be under some sort of market rule or contract, where they can respond to dispatch, if necessary. Now, usually, of course, you're still going to want to get as much energy as possible from wind plants in most cases because it's usually the cheapest, as well as cleanest energy you have available. So you tend to want to use as much of it as you can. But it is nice to be able to back them down if it's an emergency situation and it's really necessary, to do that.
Right. So I'm going to ask a question that came in on the chat box, and then I'm going to try to unmute. I don't know if it's Miss or Mr. Amu. So one that came in on the chat box relates, it looks like it's kind of a state-based question. They're asking about, are there market rules that individual states could adopt to increase access to wind's flexibility? Because you had made a statement earlier, I think, about that wind has a lot of flexibility, but the market rules aren't necessarily in place to access it.
Right. Yeah. I mean, most of the wind so far has been built to, often to meet a state portfolio standard, where you want to get to a certain percentage of wind, or various, motivations like that. And under those sort of rules, you're really just counting the megawatt hours of wind. What's the energy you're getting from wind, and you're not really assigning a value to some of these other services or the ability to quickly ramp or to provide these other services. You can do it. You kind of have to change, in some cases, the motivations that you're giving, to the utility or the whoever is buying this wind, and assigning some sort of value, because it's no different than any other contract. You're going to do what you're paid to do. So in some of the market regions now, there's move to actually create new, what they call ancillary services products, meaning in addition to just buying the energy, I will also have a market product where I will pay you for a certain amount of this sort of fast ramping or these other, potentially these other reliability services at some point. And then if you have multiple revenue streams, as you are starting to have in some of these market regions, you can certainly do that through the market. States could do it directly, but in most cases the state is not, directly running their own market.
Okay, great. I realized that people who had little question marks instead of their hand raised actually had typed their question. So this is a learning curve for me. So I'm going to go ahead and read Kelly's question, and it's, what does it mean to have wind ride-through requirements? How does that exceed conventional power? So ride-through requirements.
Sure. Well, ride-through, of course, first means that if I have a deviation in my frequency or my voltage, that the wind plant will not disconnect from the grid, and it will stay synchronized and connected to the grid And the most conventional plants also can do this to a degree, although you often have certain components, like within a conventional thermal plant, that will be impacted, like if the voltage goes to zero for a fraction of a second, even though they're what they call their relay protective settings, that are connecting it with the grid, kind of the fuses there. Even though those may ride through, it doesn't mean that some of the motors and equipment inside the plant will necessarily ride through. So with wind, they actually have requirements that are even more strict than for conventional thermal plants. And wind has to be able to survive a zero voltage event of several cycles and then ride through and still be there. So this took some doing with how you design a wind plant, how you do the electronics and so forth. But it has been tested out, and it's now a standard basically for all new wind turbines.
Okay, great. I have one or two more questions on the chat box, but I think that they will be good for both you and Jim to answer. So I'd like to go ahead and move on to Jim Caldwell, who's going to talk through the low carbon grid study. So Mark, thank you very much, but stay tuned because some of these questions are going to be for you too.
Sure, thanks.